technology come to life.
Welcome to Brainspew. Let's talk about AI. Well, a couple of other things beforehand. Our human minds are often referred to and described as computers, and they certainly are wonderful signal processing and computational devices. A key difference between our brains and the current digital computers in use today, and that is the year of the making of this video, 2016, is the methods that they utilize to accomplish those computational tasks. A digital processor, which is at the heart of a modern computer, is based to a large extent on the proposed mechanical A machine that Alan Turing conceptualized in his 1936 paper. While a computer is much more sophisticated than a Turing machine, it still retains a certain mechanical notion to the way in which it processes information. Imagine a black box with a turn crank, some inputs, some controls, and some outputs on it. Every time you turn the crank, you draw from the inputs. They can be in two states, either on or off. Now, as the inputs travel in the box, they reach a gate. If a certain gate is open, it's dictated by the controls. If a gate is open, it lets the specific input pass on to the output. And that's about it. All operations in a digital processor are done in this fashion, albeit exponentially scaled up. As such, the structure of the logic inside the box is set in stone. Well, silicone to be more specific. What changes is the information flowing through the controls, inputs, and outputs. Of course, this information has to flow from and to somewhere, so storing the information is done on other memory devices, for which we have no need to get into. A closer analogy for our brains would be a field programmable gate array, devices that are composed of logic and memory blocks, which function and interconnectivity can be reprogrammed. But even that falls short of the mark. Information in our brains is stored in analog form, which provides us with a vastly larger number of states than the digital on or off. The brain is a network of neurons that are interconnected both in serial and parallel. Beyond that, the structure of this network is plastic in its nature and subject to change. As such, the network serves both the purpose of storing the information and computing it. Those computations taking place both serially and parallel. Now, finally on the topic of AI. The way we implement AI and machine learning is by modeling neurons and neural nets on digital computers, thereby being able to take advantage of the adaptive capabilities of the model of the brain. Of course, because these networks are running on digital computers, each component has to be processed in the same mechanical, crank-driven kind of way. That means that even a relatively small network requires a tremendous amount of computational power. As you can see now, the big bottleneck to AI currently is that we're essentially emulating neural nets on hardware that is anything but native to them. It is easy to envision the powerful possibilities of AI running on native hardware. After all, look at us humans. On second hand, better not. Imagine something better. This problem has not escaped the people who concern themselves with such things. And solutions have been worked on since at least the late 1980s, when Carver Mead pioneered the idea of neuromorphic computing. And already we're seeing the birth of these technologies with IBM's just recently announced creation of the first phase-change artificial neuron. An actual physical hardware that behaves much like a biological neuron. In a package that is both incredibly scalable and low power, characteristics that are both of great importance if we want to build large neural nets that can match or even surpass biological brains. And we do indeed if we want to harness the power of AI. At that, these networks of artificial neurons would be very well matched to be linked to the more traditional Turing-inspired computational devices such as the modern microprocessor, taking advantage of both of their strengths. Now that the proof of concept is here, the creation of native hardware for neural nets at full scale is undoubtedly soon to follow. With the advances in stem cell research, artificial blood, medical 3D printing of live cell cultures and tissue, and gene editing, I can easily see 3D printed brain tissue in specific structures to perform desired computations. Needless to say, we're now witnessing the very first few breaths this field of technology is taking. But do not blink, because if it grows anything like the rest of computing has, you might just open your eyes in a whole new world. Then again, what the f do I know?